Similarly, at the end of the previous video, here K denotes a field, K of x denotes the polynomial ring with one variable x. And we define a rational function field as a set that contains the fractions of polynomials with non-zero denominator. And as I mentioned in the previous video, here x denotes a transcendental element over K, so this is not algebraic. Another important fact about the structure of a rational function field, it's every element can be represented as a fraction of relatively prime polynomials f of x and g of x. That means greatest common divisor of f of x and g of x is 1. Moreover, the polynomial ring K of x is unique factorization domain. We may consider the factorizations of polynomials f of x and g of x into irreducible factors. And thanks to this decomposition, we may also represent a function in a rational function field as a product of integer powers, they can be positive or negative, of irreducible monic polynomials. And this representation is unique up to constant a. When we have two rational function fields, which are defined with respect to transcendental elements x and z over k, they are not supposed to be equal to each other. We may identify vector space isomorphism by mapping the transcendental x to transcendental z. Vector space isomorphism. And this is why sometimes we say the rational function field. However, I think it's worth to mention that we don't have a field isomorphism always. For instance, if you consider the rational function fields k of x and the k of x square, even though we have a vector space isomorphism, this is not going to be field isomorphism. And later we will see that indeed k of x is a field extension of k of x square of degree 2. And I think this is why still in some cases we say a rational function field. Final remark I want to point out. Okay, when we have a rational function field, we can view it as a field extension, but this is not finite extension. And the base field K is algebraically closed in K of X. That means any element in a rational function field which is algebraic over K also lies in K. And its proof will be one of your homework in the following weeks. In this course, mainly we will be interested in the finite extensions of a rational function field. More explicitly, we will define an algebraic function field over K is a field extension such that it contains a transcendental element over K and if is a finite extension over a rational function field K of X with respect to this transcendental. The simplest example of an algebraic function field, of course, can be considered as a rational function field because it has extension degree 1 and it contains transcendental element. And for an algebraic function field, we will often this notation. And algebraic elements in F over K forms the subfield of F because the sums, products, and inverses of algebraic elements are also algebraic. And this field is called the full constant field or simply constant field. Of F over K. And we say K is algebraically closed in F if K is equal to the full constant field. And in the theory, often we often take the base field as a full constant field, but they are not supposed to be necessarily equal to each other. And before exploring this definition, I want to mention an analogy between algebraic number theory and algebraic function fields. So far, we have considered a unique factorization domain, K of x, and we define a rational function field as fractions of K of x. And here we are interested in the finite extensions over a rational function field. And in number theory, one is interested in integers as a unique factorization domain, and its fractions defines rational numbers, and a number field is defined as a finite extension over K. Fortunately, this is not the only analogy between algebraic function fields and to other theory. For instance, you can also study algebraic function field with the motivation of algebraic geometry or compact Riemann surfaces. However, and unfortunately, the drawback of this course will be the lack of the test of the relations between these theories. However, if you've seen any lecture about these theories, you can try to find a correspondence between algebraic function fields and other related fields. For the algebraic function fields, for the simplicity, often we represent them as a simple algebraic extension over K of x. So that means often we can suppose that f is obtained adjoining a root of a polynomial into K of x. And by this simplicity, we will prove that the transcendental elements in algebraic function fields can be characterized as follow. As usual, f of k denotes the function field, algebraic function field. So that means there exists transcendental in f. And f is a finite extension over K of x. Then it is transcendental over K if and only if f has also finite extension degree over K of z. Since here extents that are not supposed to equal to each other, we don't have to have the same extension degree here. But even though we can have the different extension degree, it will be always the finite. So in this picture, it's natural to ask if we have the similar properties we considered in this first remark. For instance, for an element, we know that it has a unique representation in terms of irreducible factors. And we want to ask the same question for the elements in a non-rational function field, in general, an algebraic function field. However, at the moment, it's not clear enough what we mean an element Z in F admits such a decomposition. Moreover, it's not even clear what we mean by an irreducible element in F. Another problem which is also related to this unique representation, given some algebraic elements, we want to find rational functions that contains these alpha i's as zeros and poles. So that means alpha I 0 in the case alpha I is a 0 of F. And if denominator is 0, we say that alpha j is a pole of phi. And in order to formulate the similar problems in an arbitrary function fields, in the next video, we will begin the notions of valuation rings and places. So see you in the next video. Bye-bye.